Scientists just completed the most comprehensive survey of the Cascadia subduction zone ever conducted, and what they found changes how we understand this fault. The megathrust isn't one continuous structure. It's divided into 4 segments. Here's what the new seafloor mapping revealed. For decades, hazard maps of the Cascadia subduction zone were built on a handful of seismic profiles collected in the 1980s. Those early surveys, limited by technology and sparse coverage, left major gaps in our understanding of the fault's true shape and behavior. The prevailing model pictured Cascadia as a single continuous megathrust, stretching some 700 miles from Northern California to British Columbia, an idea that shaped everything from earthquake drills to building codes. But as Dr. Suzanne Carbat of Columbia University's Lamont Doherty Earth Observatory explains, the models currently in use by public agencies were based on a limited set of old, low-quality 1980s-era data. In the summer of 2021, a team of geophysicists set out to change that. Their mission was to conduct the first comprehensive high-resolution survey of nearly the entire Cascadia megathrust. For 41 days, the research vessel Marcus G. Langseth sailed up and down the Pacific Northwest coast, towing a 9.3-mile, 15-kilometer digital streamer packed with 1,200 hydrophones. This floating array, stretching farther than the length of Manhattan, captured the faint echoes of powerful sound pulses fired into the ocean floor. Each pulse traveled through layers of sediment and rock, then bounced back to the surface, where the hydrophones recorded the returning signals. The process is often compared to a medical ultrasound, but on a scale that images the Earth's crust tens of kilometers deep. By the end of the cruise, the team had mapped 560 miles, about 900 kilometers of the plate boundary, collecting a data set orders of magnitude more detailed than anything before. The survey's design allowed scientists to resolve the structure of the megathrust fault in 3 dimensions, revealing features invisible to previous generations of researchers. As Dr. Carbat put it, it's the first time that a regional survey that spans almost the whole subduction zone has been conducted. This technical leap provided the new foundation for a new generation of hazard models, ones that could finally test long-held assumptions about how Cascadia behaves and what that means for the 12 million people living in its shadow. For decades, the Cascadia subduction zone was seen as a single unbroken fault, an immense threat running from Northern California to British Columbia. This idea shaped emergency plans and building codes across the Pacific Northwest. But new seismic imaging, published in 2021 by Dr. Suzanne Carbat's team at Columbia University, has upended that view. The data, collected over 41 days at sea, revealed that Cascadia is not one continuous fault, but at least 4 distinct segments, each separated by deep, buried cross-faults invisible to earlier generations. These cross-faults may act as natural barriers, limiting how far a rupture can travel during an earthquake. Dr. Harold Tobin of the Pacific Northwest Seismic Network, a co-author of the study, put it simply, "This does upgrade evidence that there are segmented ruptures. The first big takeaway is a better view of what the fault zone actually looks like. The new map shows a fault system far more complex than anyone expected. Each segment has its own character. The southern segments, off Oregon and Northern California, are marked by rough topography, subducted seamounts, and steep dips, features that may slow or stop earthquake ruptures. The Washington segment, though, stands apart. It stretches from southern Vancouver Island beneath the Olympic Peninsula and into northern Oregon. Here, the fault is smoother and dips much more gently than previously thought. The seismic images show the fault plane reaching farther east, directly beneath the Olympic Peninsula, bringing the seismogenic zone within about 50 kilometers of Seattle and Tacoma. As Dr. Tobin notes, In some areas along its 700-mile span, Cascadia is close to horizontal, much flatter than previously thought. Geometry matters. Around the world, subduction zones with flatter, smoother faults like Tohoku, Japan, are linked to the largest earthquakes. The Washington segment's shallow dip increases the potential contact area between the plates, creating the conditions for significant slip. That's the key to why the flat, shallow dip angle of the fault off Washington can host bigger ruptures. There's just a lot more fault surface area between 0 and 20 kilometers, Tobin explains. Discovery replaces the old myth of a single uniform Cascadia fault with a more detailed, evidence-based map, one that will shape how the region prepares for future earthquakes. Hazard models built on the old idea of a single uniform Cascadia fault underestimated just how close the threat comes to the heart of the Pacific Northwest. The new mapping, published in 2024 by Dr. Suzanne Carbot's team in Science Advances, reveals that the Washington segment's geometry changes the entire equation for ground shaking and tsunami risk. Where earlier models kept the main danger offshore, the updated images show the fault's seismogenic zone reaching much farther inland, directly beneath the Olympic Peninsula and within striking distance of Seattle and Tacoma. This inland shift is not minor. Subduction zones with smoother, flatter fault planes, like the one now confirmed beneath Washington, are globally linked to larger, more energetic earthquakes. The shallow dip angle means more of the fault surface is locked and able to slip all at once, increasing the amount of energy that could be released and the area over which shaking could be felt. As Dr. Harold Tobin of the University of Washington and the Pacific Northwest Seismic Network explains, for places like Tacoma and Seattle, it could mean the difference between alarming and significant. Early simulations suggest that peak ground accelerations for Puget Sound cities may be higher than previously estimated, though the precise numbers are still under review by USGS and state agencies. The new geometry also shifts the likely source of tsunamis closer to the coast, reducing warning times for coastal communities. For a region home to more than 12 million people, the implications are substantial. These findings provide a new framework for how engineers, emergency planners, and residents must think about earthquake and tsunami risk, not as a distant offshore event, but as a hazard that now reaches much closer to home. On January 26, 1700, the Pacific Northwest was rocked by an earthquake so massive it altered the landscape. Scientists estimate its force between magnitude 8.7 and 9.2. The evidence remains in Oregon's ghost forests, cedar trunks killed when the ground dropped, letting seawater rush in. That same night, a tsunami crossed the Pacific, striking Japan with no warning and no local quake to blame. Indigenous oral histories from the Makah, Ho, and Quileute peoples recall violent shaking, rivers shifting, and villages lost to waves. These stories, passed down for centuries, align with the geological record. This was the last full margin rupture of the Cascadia subduction zone. Tree rings, sediment layers, and tsunami debris reveal a cycle. Earthquakes of this scale hit every 300 to 500 years. It has now been 324 years since that event. The U.S. Geological Survey estimates a 37% chance of a magnitude 7.1 or greater quake on this fault within the next 50 years. Recent research shows Cascadia isn't a single fault, but at least 4 segments, each with its own risk. The Washington segment, smoother and flatter, could produce the largest events. How the next rupture unfolds will shape the future for over 12 million people. New seafloor mapping does more than update scientific models. It sets in motion real-world changes for over 12 million people living in the Pacific Northwest. State and federal agencies are now working to translate these findings into policy. beginning with the Washington State Building Code Council and its scheduled 2025 code cycle. This process draws directly from the 2024 Science Advances study led by Dr. Suzanne Carbot, which revealed that the Washington segment of the Cascadia subduction zone is smoother, flatter, and extends farther inland than previously thought. For engineers and emergency planners, this means revisiting the assumptions that have guided seismic design for decades. Revised hazard maps, incorporating the new fault geometry, are already under review by agencies responsible for building standards and emergency preparedness. These updates will shape everything from the seismic retrofitting of schools and hospitals to the requirements for new construction in cities like Seattle and Tacoma. For homeowners, the implications are concrete: reviewing the status of home retrofits, subscribing to the USGS earthquake notification service, and monitoring revised hazard maps as they become available on state emergency management sites. While the probability of a magnitude 7.1 or larger earthquake in the next 50 years stands at 37%, a figure based on centuries of geological evidence, not prediction, the new framework empowers communities to take informed steps. The science to policy pipeline ensures that as our understanding of the Cascadia fault grows, so too does the region's ability to prepare and adapt. Today, more than 12 million people live above a fault now understood as 4 distinct segments, not one uniform line. As Dr. Suzanne Carbot's 2024 Science Advances study confirms, these new maps overturn decades of assumptions. Preparedness begins with understanding, and awareness, not fear, shapes resilience. Share your thoughts below.